Hello everyone. In the last lecture, we have started looking into self-potential method of electrical geophysical investigation. Right? Self-potential method, as we have learnt, is a passive method in which we are just going to measure the naturally present electrical potential. Towards the end of the last lecture, we had seen this slide. That means how we are able to estimate the limiting depth of differently shaped anomalous bodies below the surface of the earth. So, that is based on half anomaly width. So, half anomaly width multiplied by 1.305 if it is a spherical ore body is going to be the limiting depth. That is, until that depth the anomalous ore body is expected. Similarly, for horizontal cylinder, vertical cylinder, steeply dipping sheet of anomalous body. This is what we had seen in the previous lecture. Now, let us try to understand what are all the different applications of self-potential method. Right? Mostly self-potential method is used in understanding the metalliferous mineral deposits. If you are a mining engineer or a geology student, application toward this will be of greater interest to you. And they are also used in hydrogeological investigations. Right? If you are a geologist or a water resources engineer, understanding the subsurface groundwater flow can be understood from self-potential method. Also in geothermal exploration, since self-potential is also related to temperature gradient, it is also used in geothermal prospecting. Understanding the integrity of the embankments of tanks and dams, it is of greater interest to geotechnical engineering. Then lastly, it is also used in understanding groundwater pollution. Right? Let us see some advantages. Right? What are all the advantages? In fact, we had started this method by saying this is the most simplest geophysical method. Right? So, the greatest advantage is very simple to carry out the investigation. Since it is cheap, it can be done very quickly. Why we are able to carry out the survey very quickly? We are going to just use 2 electrodes and we are going to measure the potential between them. Right? This is the ground surface, just we are going to use 2 electrode, that is M and N electrode. So, it can be survey can be done so rapidly. Once if you can run the survey very rapidly, it is going to be a cheapest method. That means cheap in the sense in terms of cost I am referring. Right? Cost is very less. Right? It is going to cost very less if you are going to do the survey. And equipment we are going to use also is very simple, since we are going to use just 2 electrodes and we are going to measure the potential between that. Right? So, it is a cheapest and non-expensive method, and as we had begun this method by saying this is the most simplest geophysical method. So, these are all some of the greatest advantages of self-potential method. What are the disadvantages? This method has got disadvantages too. Very sensitive to noise. What do we mean by noise? Some local variation, right? The surface of the earth, you are keeping M and N electrode here. If there is some anomalous material just beneath the electrode, non-polarizable electrode, that is going to lead to lot of noise, in the sense the measured value may not be representative of what is present below the surface. Right? This is one kind of noise. Then quantitative interpretation is little bit difficult. Many a times interpretation is qualitative. Right? Though we had a look into little bit into inversion as well as how we can estimate the limiting depth based on the half anomaly width, they are not often carried out. And Another greatest disadvantage is it is meant for very shallow investigation, because the naturally present electrical potential from deeper depths, right, beyond let us say 100 meters cannot be sensed by the electrodes kept at the surface of the earth. So, generally we are able to understand the subsurface of the earth up to 30 meters, maximum maybe 30 meters. This is one of the disadvantage of this method. Let us look into some applications, right. How we can understand the presence of major geological structure below the surface of the earth, right. So, there is a discontinuity, right. This discontinuity is picked up by the cell potential method, right. That means cell potential on this side is comparatively higher compared to the right hand side of this discontinuity. Hence, cell potential method is able to pick up the variation in the cell potential caused due to a major disturbance, probably the occurrence of groundwater on the left side is very different from that of the right side. That is causing minor change in the cell potential, probably indicating the presence of a discontinuity. However, simply by looking at the cell potential profile, we won't be able to identify the discontinuity. We need to deploy other tools. But what is interesting here is even a major buried geological structure is able to give contrasting cell potential between this side with the other side. Then the next is, let us have a look into a interesting study carried out by this person Gallas as a case study. Here they had tried to make use of cell potential measurements to understand whether there is any leakage in a dam, right. The dams are of two different types. In one earthen embankment dam, we may have a core wall. Certain earthen embankments we may not require a core wall. So, this is the side of the reservoir where water is stored, and since water is at higher head, right, there is a core wall. Water will try to rise here from below the core wall, right. Let us imagine this is the foundation of the core wall, and since the head is much higher, on this side water will try to rise and try to flow towards the downside of the slope of the dam, right, earthen embankment, right. Now, what happens beneath the surface of the earth is the presence of the fluid, which means in this case it is water, right. The passage of water through the porous medium itself produces some electrical potential, right. Hope you can recollect, we had seen the process of generation of electrical cell potential at the beginning. One such process is this electrokinesis, right. So, along the pathway of fluid movement or the groundwater movement, interaction in the pores with the electric double layer results into electrical potential. So, what is electric double layer, right? We have seen already the surface of a mineral normally is negatively charged, right. Suppose if you consider this as a small grain, surface is negatively charged, due to which the water passing through will have all the positive ions surrounding the surface of this, right. You will have a kind of cloud of positive ions. After some distance, you will have both positive and negative ions. The flow of water tries to push the positive ions further, but they try to stick towards the negatively charged surface. This leads to a formation of a double layer. This formation of double layer itself generates some cell potential, as you can see in the diagram, right. what happens here is the surface, right, here is the void through which water is moving, and as I had shown you here, surface is negatively charged. As the surface is negatively charged, all the positive ions in the electrolyte or the water is forming a cloud here. Mostly this region has got positive ions, though they are in water, right. These ions forms a cloud because negative ion here attracts the positive ions, right. And as you move away from the negative surface, here you have both positive and the negative ions, right. So, you have a kind of double layer. What is the double layer? Here you have negative ions and here you have the positive ions. This itself leads to generation of electric potential, right. So, here is the surface, clay surface, this is the distance away from the surface. If you look at the positive ions are very high closer to the surface, because this surface is negatively charged. The entire surface you have only negative ions, due to which more positive ions, almost negligible amount of negative ions closer to the surface. As we move away and away, then beyond certain distance only you have both the positive and negative ions. Okay. So, that is the distance which is called as double layer, right, double layer thickness. That means the distance from the negatively charged surface beyond which you have both positive and negative ions in equal amounts. Until that distance we call it as double layer, right. So, this double layer formation itself generates some electrical potential due to the gradient. So, you have a gradient variation, that is why it is called as electrokinesis. So, this leads to the development of electrical potential, right, depending upon the situation, subsurface situation. Here you see, right, water is flowing in this layer, right, and the way in which water flows in this region is different from that of the water that is flowing in the white colored layer. Okay. So, here is the water flow. As the water flows, the ions in the next layer tries to also follow the movement of water, right. So, here you may have the positive ions. As the water moves, right, the positive ions also tend to follow the water that is moving in a more permeable lower layer. This leads to the potential gradient, as you see here, low potential gradient in this zone, comparatively higher potential gradient away from this, right. So, this process itself leads to development of electrical or variation in the electrical potential which we measure at the ground surface, right. So, making use of this theory, this researcher Gallus has tried to understand the seepage from a dam. As you can see on the left hand side diagram, right, this is a picture of a dam. Somewhere here they have detected the leakage over the entire area. At the surface they had carried out cell potential measurements. So, here is the location of the dam, it is a plan, right. Here you see in this diagram you see the contours showing equal cell potential, but somewhere in this zone you see a kind of anomalous values, right, compared to this area, right. That means wherever you have this red, little bit of red and orange color, there seems to be some anomaly. That is what they have indicated here. So, anomalous trend of variation in cell potentials, right. Probably that is the direction in which there is going to be a leakage. So, this is the dam, this is the upstream side, this is the downstream side, right. So, here you can see the spillway, right. So, in this diagram, so this diagram we had seen already. Here just across the dam, right, this is the location of the dam. Here you can see the locations along which there is likely to be possible presence of kind of weaker zone along which the water tends to move through. Here are some directions where there is a significant trend or variation in the values of cell potential, possibly associated with the differential groundwater flow, right. So, this is how cell potential method has been used to detect the possible zones along which leakage takes place in a earthen embankment, right. They had also carried out another study, same this Professor Gallas has carried out another study in a site where they are storing some mine waste, maybe of interest to mining engineers. So, here is a dam where they are storing the tailings from after processing the ore, after beneficiating the ore recovered from a site by a beneficiation plant, that will lead to some waste as a slurry. This slurry is normally conventionally stored on in a surface dam, right. Of course, by taking care of preventing leakage, all care has been taken. Here they are storing the mine waste as a slurry, and at the same site they also have another dam where fresh water is stored, right, for different purposes, right. So, over there, right, that means here is the tailing storage and here is the water storage, right. So, over there they had conducted, that means in this zone they had conducted a cell potential survey, mainly to understand whether there is any leakage from the tailings as well as from the fresh water reservoir, right. So, that is why all these yellow dots are the locations along which cell potential method survey has been carried out. So, here are the results, right. This is this is the tailings pond, this is the tailings pond, this is the water storage pond, right. So, here this is the location of the storage of mine tailings, right, and here you can see the picture also, right. This is the dam. So, this is the dam water storage, water is stored on this side. In both the cases you can see the map of cell potential distribution, which is not uniform. There are some zones, right. In this case cell potential is little bit higher along the zones where there is leakage of water, right, probably caused by shift in the double layer, which the theory we had seen just now, right. Probably due to that there is a zone where you have this color, right, slightly dark red or orange color indicates higher cell potential value. They are the pathways along which there is some leakage. So, we could detect the leakage along these principal paths, right. This is from the tailings. So, there is some leakage somewhere here in this direction and also along this direction. Coming to the water storage structure, from the water storage structure too there is some leakage here as well as here, somewhere from the middle part as well as from the northern part there is some leakage. So, very easily we are able to understand about the integrity of the earthen embankment in this case. The same can be carried out in other earthen dams to understand whether there is any leakage or not. This, as you know, it is completely a non-invasive method, right. We are not digging or excavating, we are just keeping two electrodes at the surface and we are measuring the potential difference between them, right. So, this is how they have understood how the dam is functioning. In this study, right, given in this website of University of Texas, these researchers have carried out to understand how carried out a study to understand how groundwater seepage is taking place in a karst terrain. Karst terrain is a terrain associated with limestone, right. Limestones are rocks which are of calcium and carbonate composition. This calcium carbonate is tend to dissolve with the ground, with the water, right, especially even the rainwater is slightly acidic. Due to this rainwater will dissolve the limestone, leading to formation of a karst topography, which is a topography known for presence of some circular depressions, where when the water begins to get collected after rainfall, the water will slowly dissolve and the circular depression will further deepen, leading to formation of vertical holes, and adjacent vertical holes also gets connected below the surface as caves, right. Over there they had made use of cell potential survey along the embankment of a reservoir. So, here is a reservoir. Along the embankment of reservoir, they have carried out two profiles of cell potential measurement. So, from the cell potential measurement, here too they had identified certain locations where cell potential is much higher, right. These two, the dark black color and gray color are the two profiles. Here you can see the survey has been done in two parallel lines, right. So, the region where we had very high cell potential, that means somewhere here as well as here, these are all the possible locations where there is likely to be some seepage from the dam, right. That means, right, here is this is the north and this is south. So, this profile is for this particular stretch. So, somewhere here this is north, somewhere here there is some leakage, right, where the rest of the embankment is reasonably fine, right. So, here what they have made use of is they had also carried out electrical resistivity. The bottom, this diagram is electrical resistivity and this one is the cell potential profile in millivolts, right. This is depth. This survey was conducted by electrical resistivity tomogram ERT. So, this is cell potential method. This is a cell potential method at the top, right. So, here they had made use of both electrical tomogram, that is electrical resistivity method, as well as cell potential method, right. So, where the resistivity will be less in the zones where there is lot of groundwater. So, here there is a seepage location. So, the values of resistivity is very less. Similarly, wherever there is more water, more electrical potential, that is what is indicated by the higher SP values. So, beneath the high SP values, there is likely to be some leakage of groundwater. That is what has been reported in this study. Here is a study carried out by these people, a very interesting study where they had made use of, you can see the scientist sitting in a boat, right, trying to understand how the cell potential values measured at the bank of a river, right, help to understand the interaction between the river as well as the adjacent groundwater. Suppose if I draw the cross section of a river is something like this, right. Here is the river, right, this is water, this is land part. Here if I continue to draw the river water level, and here is this is groundwater, this is river, river water and this is groundwater. So, by making measurements along the bank of the river, as you can see here, they have carried out a profile for several kilometers, right. Here is the scale given in meters. So, this itself is for almost 15 kilometers, right. Along the bank, survey was carried out by electrical potential, right. Here too, they have deployed a new technique of waterborne gradient, right. That means the electrodes are attached to a boat and then we measure the potential difference between this and the electrode that is moved on the bank of the river, right. So, here is the values of cell potential, right. Cell potential values are comparatively less in this reach, whereas here there is it is much higher. So, when the values are much higher, the interaction between surface water and groundwater is much more significant, isn't it? Because only when the river water moves through the bank, cell potential will be much higher. That means, in the first stretch interaction is less, whereas in the remaining stretches there is a strong interaction between the surface water and groundwater. So, this is one application of cell potential method. So, we had a look into different methods of cell potential in the previous lecture. In this lecture, we commenced by looking into how we can estimate the depth of the buried ore bodies from the half anomaly width, right, from the half anomaly. This is what we had seen. Then we had a look into applications as well as advantages and the disadvantages of the method. Then we had a look into some interesting case studies carried out around the world. Here we have understood how cell potential method is able to help us to delineate the buried major structures. Here we try to understand how cell potential method can be used to know about the leakage beneath the dam, right. Here that is because of this electrokinesis due to the formation of double layer. This double layer also gets changed during the seepage of groundwater, which helps to understand the locations of seepage from the dam. Similarly, in another case, we try to understand how there is seepage is taking place from a water reservoir, and toward the end we had also seen how combination of both electrical resistivity as well as cell potential method is being used to understand leakage from a reservoir. In the last study, we had seen how we are able to understand the interaction between groundwater and surface water by cell potential method. Thank you very much. We will see during the next lecture. Thank you so much.